this movie, we look at 3 types of structural isomers: functional, positional, and chain isomers. All structural isomers are 2 or more organic molecules which have the same molecular formula as one another, but which differ in their structural formulae. How they differ depends on which type of structural isomer we're speaking about: functional, positional, or chain isomers. We look at the definition of each of these and some examples. Functional isomers are 2 or more organic molecules which have the same molecular formula but different functional groups. Esters and carboxylic acids, which have the same number of carbon atoms as one another, are always functional isomers of one another. Let's take methyl methanoate and ethanoic acid as examples. You should pause the movie and draw the structural formulae and give the molecular formula of these 2 organic compounds before I show you these. Only resume this movie when you've tried that yourself. We can see that methyl methanoate is an ester. So that means that it has the ester's O atom joining the 2 sides of the ester, one which came from the alcohol and the other one from the carboxylic acid. It's also got a double bond O. That's the structure of an ester. So we know that that's inside there. We'll do the rest just now. Ethanoic acid is a carboxylic acid. That tells us that it has the carboxyl functional group, COOH. What about the rest? Methyl is CHHH. We can see that that carbon has 4 bonds, so that's finished. And then meth, so there's only 1 carbon, a methanoate. This one has 1, 2, 3 bonds so far, so it needs another H. So there we have methyl methanoate or methyl methanoate. Ethanoic acid, Eth means 2 carbons. There's 1 of them. Let's add in the other one. And then, of course, we must check that each carbon has 4 bonds. This carbon already has 4. But this one only 1 so far, so we need to add in another 3 hydrogens. So that is the structural formula of methanoate and that of ethanoic acid. What about the molecular formulae? And they have the same molecular formulae as one another, which is why they are isomers of one another. What is that molecular formula? C2, you can see in both cases, they're 2 carbon atoms. And then O2, in both cases, 2 oxygen atoms per molecule. And then what about the H's? Let's count them. 3, 4 in this one. And sure enough, 3, 4 in that one. They have the same molecular formulae, and yet you can see that they have quite different structural formulae. And in what way are they different? You can see that they have different functional groups. That's why they're functional isomers. How about positional isomers? Positional isomers are 2 or more organic molecules which have the same molecular formula, but different positions of the side chain, substituents, or functional groups on the parent chain. Let's take 2 examples of positional isomers. Firstly, 1 chloropropane and 2 chloropropane. Pause the movie while you draw the structural and molecular formulae of these 2 compounds. Both of these are haloalkanes, so they're saturated compounds with a halide inside them. And we can see that they have 3 carbons each, propane. So let's start by drawing that. And we can see that they both have chlorine in them. The way in which they differ is where that chlorine is. So in the first one, we have chlorine on carbon 1, whereas in the second, chlorine is on carbon 2. So we can immediately see why they're positional isomers, because the position of the substituent is different. Let's fill in the hydrogens, and then we can see why they're isomers. In other words, they have the same molecular formulae as one another. As I said before, they're saturated, they're only single bonds, and we must make sure that each carbon has 4 bonds. So, what's their molecular formulae? C4 in both cases, H, 2, 4, 6, 7. Same here, 3, 4, 5, 6, 7. And then 1 chlorine. So they share a molecular formula, they're isomers, even though they do not have the same structural formulae. That's why. They're not identical, they're isomers. And how do they differ? In the position of these substituents. Let's take another example where the position, now not of the substituent, but of the functional group differs. So here we have but-2-ene and but-1-ene. They're both butenes. In other words, they're both alkenes. They have a double bond in them. And they're both butenes. They have 4 carbon atoms. How do they differ? Where that double bond is. So let's start by just drawing the 4 carbon atoms in each case. And then let's immediately put in the thing that's different. The functional group here is at position 2, meaning between carbon 2 and 3. Whereas in but-1-ene, it's on the first carbon atom. In other words, between the first and the second carbon atom. That is where we get the double bond. Let's fill in the hydrogens, making sure that each carbon has 4 bonds. So you can see this carbon already has 3. So we must only put in 1 hydrogen. It doesn't matter whether we put it there or there. Same with this one here. This already has 3, so we must only put in 1 hydrogen. Let's put it there. Doesn't matter, we could have added it there. And this one needs 3. Each carbon now has 4 bonds. Let's do the same over here. 1, 2, 3, another H here. 1, 2, 3, 1 more H. Doesn't matter if we put it up there. What about the molecular formulae? Because they're butenes, we know, well, from the but, it must be C4. And because they're alkenes, it must be H8, because the general formula of the alkenes is CXH2X, or CNH2N if you prefer. But you can go and actually count it if you like, and you will see indeed there are 8 H's here, and 2, 3, 4, 5, 6, 7, 8 H's there. So they have the same molecular formula, even though their structures are not the same. How are they different? In the position of the functional group. Notice, it's not in what the functional group is. Then it would have been a functional isomer. Like here, we had different functional groups between the two that we are saying are isomers of one another. Here we have the same functional group between the two. And so they're not functional isomers. They differ in where that functional group is, the position of that functional group. That's why they are positional isomers. Now, you should notice that the definition of positional isomers does also allow for the isomer to differ in the position of the branches attached to the parent chain. Funny enough, though, there's a bit of vagueness here in IUPAC naming, in that there's an overlap between positional and chain isomers here. If 2 or more isomers differ in the position of the alkyl branches, like in this example here, we rather refer to them as chain isomers, even though this definition of positional isomers would suggest that we could also call them positional isomers. Chain isomers are 2 or more substances which have the same molecular formula but different types of chains, or, as in this example, different positions of the alkyl chains. Let's use butane and 2-methylpropane as another example. Pause the movie while you give the structural and molecular formulae for these. Butane, very simple. But means 4, it's an alkane, so nothing else. saturated with hydrogen. 2-methylpropane, a little bit more complicated. Prop means 3 carbons. And then we have 2-methyl. That means on the second carbon, we have a methyl group, just 1 carbon. And then we must just fill in with hydrogens so that each carbon has 4 bonds. So clearly they don't have the same structural formulae as one another. This one has no branches, this one has a branch. But what about their molecular formulae? Each case, they have 4 carbons, C4. What about the hydrogens? You can go count them, and in any case, you wouldn't even need to count this. You know from the general formula of an alkane that this must be, if this is N, 4 is N, this must be 2N plus 2. In other words, 2 times 4, 8, plus 2, 10. Go and count them. 3, 4, 5, 6, 7, 8, 9, 10 indeed. And go count these, you'll also see 10 of them. So, in summary, we've studied 3 types of structural isomers. For all of these, the term structural isomer refers to 2 or more organic compounds which have the same molecular formulae as one another, but which differ in their structural formulae. In functional isomers, the 2 or more compounds have different functional groups to one another. In positional isomers, they have different positions of their substituents, functional groups, or branches, although for alkyl branches that would rather fall into the next group, which is chain isomers, which have different types of chains, for example, branched and unbranched chains, or different positions of the alkyl branches.